Okay, welcome back everybody. We're gonna keep talking about the sufficiency principle. We'll look at another example. We'll talk about the two experimenters and what experimenter 2 would do. I'm gonna offer you some extra credit as well. I wanna point out that not all the extra credit, I'm not gonna write it up as an extra credit assignment. I'm not gonna tell you exactly what to do. That's a part of the extra credit assignment. Now, if you wanna ask questions about it, of course you can. And review session is a really good time to do that. We can go through as many details as you want during a review session. Everything is fair game. Midterm on Wednesday, and so be here on time. I'm going to be handing out the exams face down, and if you want the full 50 minutes, you'll be here on time. There'll be one instruction. It's to write your name on the exam. So don't be the one person that doesn't do that this semester. If there's two of you, it causes real problems. Not that big of a deal, but we can't overcome it. The other, I guess, instructions is it's going to be closed book. It's going to be closed notes, so you'll bring a pen or a paper. I'll have scratch paper for you, but if it makes you feel better to bring some, you can do all of that. Tomorrow we'll do a review session at 5:30 in the normal place. And I call this the yes, no, maybe review session, where you can ask me what's on the exam. And I'll try to tell you what aspects of something I might ask about. This exam is not meant to be overly difficult. It's going to mimic your homework, so if you want to practice, read through the book, work examples, work the examples in the book as well, rethink about your homework. So there shouldn't be any great surprises on this exam. Any questions? Perfect. Okay, let's jump back into the sufficiency principle, and then I'm going to get into something called the factorization theorem. And if you're like me in grad school, you've already figured it out, what the factorization theorem says. The factorization theorem concerns this statement right here, where we know from the sufficiency principle that if T of X is sufficient, then this conditional distribution, which is really just the ratio of these two distributions, is a constant with respect to theta. I left a little bit of a space right here because if you want to see this probabilistically, if you saw this statement right here, you'd say there's a problem. You'd want to probably cut T of X in here, the joint distribution, so that it looks like, you know, the typical conditioning formula that you have. But this isn't any extra information, and so we don't need to write that in. So technically, this is going to be conditioned on theta, but the statement is that if T of X is sufficient, this is going to be a constant with respect to theta. What that really means is these two distributions have the same shape, i.e., everything that concerns theta cancels out in this ratio. So that means that something must factorize with respect to theta and cancel out. And so this statement right here requires you to know what T of X is to be able to verify it's sufficient. And on the midterm, I'm just going to hold you accountable for that statement. I won't hold you accountable for the factorization theorem, and we'll try to prove it. I don't think we'll get through the full-blown proof, so I'll do the easy part, and then on Friday when we come back, we'll do the other side of the proof. I want you to look at that in the book because it concerns transformation of variables, and in my experience, people get a little bit confused with the notation. I'll try to clarify that on Friday, but working through these things is part of your job as well. Be thinking about it. Okay. Let's start with an example. So this example. Oh, I also want to say, this word right here, principle, is one of the words that I see most commonly misspelled. So the question is this principle or principal? The first one. Yeah, very good. So I see this all the time. So it's not principal. So that's like the person that was in charge of your elementary school or something like that. And the way I remember this is the principal is supposed to be your pal. So it's a person. So It's the number one thing. It's the thing that's like on top of everything. Okay, the principal of your school was never your pal. Certainly wasn't mine. So, no matter how hard I tried. So, it's principle. So, these are ideals. And I kind of like this ideal, and this is a non-controversial ideal, I think. Okay, enough about that. Oh, let me say one more thing. If you're doing principal components or something like that, if you've ever heard that, that's the principal. And that's the other way that I see this confused all the time. So I see this written down as principal components, and they're not principal per se. I don't. Anyway, just be careful with that stuff. It lets me know you're a room if I see it written down. Okay, let's jump to this example. So I'm just going to make a quick statement that I know what is sufficient. And we're going to apply this thing right here. And we'll see a lot of illuminating stuff come out of this example. And so I'm just going to write down f of x given mu. And I'm going to stop denoting sigma squared in here, just to let you know it's a constant. So normally I'd write conditional on sigma squared. And when I see this sort of notation, I have to ask myself, what is this distribution? Is this you've marginalized out sigma squared, or are you just not writing sigma squared? And usually the formula gives you some understanding of this. I'm just going to write it using this notation just because I want us to just focus on mu. This would look like this. I goes from 1 to n, 1 over square root 2 pi sigma e to the minus 1/2 xi minus mu squared over sigma squared. And when I see the right-hand side, now I know that that does concern sigma squared. It's in the equation. So my notation is denoting sigma squared as a constant and it's given to you. Again, be careful. Not everybody uses the exact same notation. And so this is the joint sampling distribution, where cap x is just this vector of IID replicates. And I could simplify that a little bit. I just want to point out to use this, and this is kind of like the straightforward way of maybe writing down what this joint distribution, and we're invoking conditional independence by doing it. Computationally, this thing is a mess. And so if I saw this equation and I was supposed to go to a computer, I would freak out. So actually, I wouldn't freak out in this case. I would know what to do, and I would apply the sufficiency principle. So this is problematic because it includes a product, and it has this E sitting right in here. So computationally, both of those things will cause you nightmares if you code that up. So granted, if you had mu's close to the xi's, this thing probably wouldn't blow up too much. And if n was small, maybe computationally it wouldn't be too problematic. But if I try to use it in general, if I use bigger n, and I have a lot of x's in here, something's going to go wrong on my computer. So I'd be very weary about encoding this. I'll say more about that in a moment. Does anybody know what the sufficient statistic for mu is? It's x bar. So we've been using that forever. So we know, we might know, P of x equal to x bar, the arithmetic mean, is sufficient. In a second, we'll know for sure, because we'll apply the definition. So quickly, what's the distribution of x bar? We also know it's normal. And it has two parameters. Mu. There you go. All stuff you know. That's the distribution of x bar. You should know this off the top of your head and be able to verify that. Okay, let's apply the formula and just verify it. But we'll get a little bit more than just a verification we'll start seeing the factorization theorem at work. So we'll just write this down, f of x, given mu divided by f of x bar, given mu. And this right here is tx. We'll write it down in terms of its full-blown glory. This is going to look like 2 pi sigma squared. I'll drop that all inside the square root, minus n over 2. So I'm just doing some simplifications, and I'm using that formula that's on top right there. So that's the normalizing constant. Keep in mind, if you did not know sigma squared, this term's not constant anymore. It involves the sigma squared. Since we know sigma squared, this will be a constant. E to the minus, I'll write it down like this, 1/2 sum of the xi's minus mu squared over sigma squared. And then the denominator is just going to be 2 pi sigma squared over n. This is to the minus 1/2 e to the minus 1/2 x bar minus mu squared divided by sigma squared divided by n. If like, I'll put my n right there. Usually I put the n there when I'm going to take a limit, just so I can remind myself it's part of the limit. So right now that notation is just a little bit superfluous. And so I can simplify things a little bit. I'm just going to rewrite this a couple times. So let's just give ourselves some room and just chew on this bit for a bit. So this is going to look like this. This is the exact same thing. E to the minus 1/2. I'm going to do things that I know how to do. I know this thing is centered around x bar. How do I know it? Because I've done this problem before. And I can see where everything's centered. And so you've also probably done this as well and included in this x bar. So I'm going to just add x bar and subtract x bar in here. So this is just a funny form of 0 that were included. Squared divided by sigma squared. Right here. And there's a sum that somehow I mysteriously lost. And so I'm just expanding that. I'm going to put these in braces and consider these two terms. And I'm going to expand out this square. So this right here is e to the minus 1/2. Just write this out in terms of all of its terms. Later on, we'll just do this a little bit faster. But this is going to be sum. I goes from 1 to n, xi minus x bar squared. Write this over sigma squared. Plus the cross term. There'll be 2 of those. Xi minus x bar minus mu. And then I've got the other term. X bar, it's going to go I goes from 1 to n. This will be sum of the I goes from 1 to n, x bar minus mu squared. All of these are divided by sigma squared. So same exact thing. Somebody help me out. What's this? That's 0. So you can verify this. This doesn't have the index there. You can drag this outside. We'll do this exactly once in this class. Just to look at this term, most of you know that this is 0. So this thing right here just looks like sum of the xi's minus n times x bar. So this is a constant. I'm going to sum it n times. So that's that. N times x bar is sum of the xi's. Sum of the xi's minus sum of the xi's is 0. So sum of the residuals is always 0. So this thing is 0. this thing is going to sum up n times right here. So I'll just write this out. This is going to be sum. I'll just break this into two terms right here. This will be sum of the xi's minus x bar squared divided by sigma squared. And I'm just going to factorize this out from that. This will be e to the minus 1/2. This has no index on I, so I'm summing up this constant with respect to I n times. So this will look like n times x bar minus mu squared divided by sigma squared. And I'll just do myself a favor and take that n and bring it down over here. So I'll plug everything back in right here. So this is equal to 2 pi sigma squared minus n over 2 e to the minus 1/2 sum of the xi's minus x bar squared over sigma squared times e to the minus 1/2 x bar minus mu squared over sigma squared divided by n. And this will be divided by the same thing in the denominator. So 2 pi sigma squared to the minus n over 2 e to the minus 1/2 x bar minus mu squared over sigma squared over n. And so we see some immediate cancellation right here. Those two things cancel each other. No surprise. And so we're starting to see the factorization theorem at work right here. Something factorized. And I'll tell you more about that in a moment. So this whole thing right here, this is just a side. This is just going to be 2 pi sigma squared. You could do a little bit of simplification if you wanted to, but I'll leave it like this. E to the minus 1/2 xi minus x bar squared over sigma squared. And there's a sum. These are those squared residuals. You can't simplify that. So this is this conditional distribution. This thing is just f of x given x bar. That's what that distribution is. So going back to the two experimenters, experimenter 1 gets to see all the xi's. They also get to see x bar. They can compute that trivially. And experimenter 2, in that group that we were studying, can sample from this distribution. So let's just talk about that for a moment. So what is this distribution? Looking at this part's not going to help you. It doesn't involve most of the things that you're interested in. The random variables are all up here. So xi's are random right here. And so I just want to point out x bar is fixed. So this is a constant. So this is being conditioned on right here, and so it never changes. So this is equal to some number. It's going to be the number that experimenter 1 can compute. What distribution is that? It looks kind of like a normal, right? And so obviously I set you up to say that. It's kind of like a normal, but there's something different than a normal distribution. So normals look like this. And so if I sample xi's out of this formula, you can write in the normalizing constant if you want. So this is going to be, I'll put my sigma squared in there. Raised to the n. Normals look like this. So very similar to what we see over there. So if I take the xi's out of this thing, right here, if I sum these xi's that I get a collection of n of them, do they have to equal to mu? No. They're close to mu. So the sum of the xi's, or at least x bar, out of this thing will be very close to mu. And as n gets bigger and bigger, it gets closer and closer to mu. But it's never going to be exactly mu. With probability 0, it's exactly mu. This, however, the xi's that you get out of it are constrained such that the sum of the xi's is exactly x bar, which is different. So this is kind of like a normal distribution. The xi's can't be any old xi's that sum to x bar. So I can't have xi's that look like this. Let's say x bar is somewhere over here. I can't have a whole bunch of the xi's over here and then one way over here. And such that it sums up to x bar, because that's not going to be distributed according to this. So sigma squared is still telling you something about the relationship and how far the xi's can be from x bar. So that's kind of pulling them in. So it can't be any old sum of the xi's divided by n that's equal to x bar, but rather they're distributed according to this shape, whatever that is. So what would experimenter 2 do to sample from this distribution? This is the part I didn't get. It's like, that's a weird distribution. Where's this number table? I want to see that. So it's kind of just thrown out there as this hypothetical. What would you do? Let me tell you what I would do. Metropolis. So to do this. This is a perfect example of where Metropolis might be useful. And so to use Metropolis, I need some sort of a proposal distribution. This is why I assigned that problem, so at least you are familiar with the algorithm. So I'll just make a note. In the context of that proof, experimenter 2 can use Metropolis-Hastings to sample from f(x) given x bar. That's this thing. And this is fully normalized. I wouldn't know off the top of my head if that's the correct normalizing constant. If he just showed me the kernel, but because we derived it and we didn't throw anything away, that is the correct normalizing constant. So it would look something like this. So the Metropolis-Hastings algorithm would be this iterative algorithm. It's going to iterate some large number of times, so I'm going to run this until it's converged. That means the distribution isn't changing as I continue to run it. So what that would look like is just one. I'm going to propose x's from some proposal distribution, g, of the some distribution over x's. My proposal distribution has to be chosen such that it always adheres to this constraint, where all of my x's sum to something that's correct. So all of my x bar out of that is fixed at whatever experimenter 1 sees. So I'm going to just say I can write this down in a Markov fashion. So I'm going to say this is t minus 1 right here. And there's a 0th step where I have to initialize everything. Initialize all of my x's at the first iteration. Now I'm going to say a little bit more about this, but your extra credit assignment is to be able to code this thing up. So 2, I'm going to come up with this Metropolis-Hastings decision rule, and it's going to look like this. It's the minimum between 1 in whatever my target distribution is, f of x star, given, I'm going to say x bar, just so I have this same thing. This is a constant. This never changes. And I'm going to compare this to f of x at my last iteration. X bar n. This is that same exact constant right here. So the only thing that's different in this formula right here, this part of the ratio, is which xi's am I plugging in. And then I'm going to have to account for my proposal distribution. This is going to be g of x star, what I proposed. I'm going to do this in a Markov fashion. And here's the reverse proposal. Again, if you want to know more about this algorithm, review session is a good time for that. And then I'm going to accept my proposal with this probability. So the last step right here is just flipping a coin with this probability. If the coin lands heads, I take my next iteration is my proposal. Otherwise, I stay at the same location. So this is going to look like this. xt is either going to be x star. Remember, these are vectors of numbers. Or it's going to be where I previously was, and this will happen with probability alpha, and this will happen with probability 1 minus alpha. So what a lot of you wrote down for your homework is you generate a uniform, and if that uniform ducked alpha right here, then you accept it. That's the inverse CDF sampler for flipping a coin, sampling it Bernoulli. So these are just these 2 steps. So let's just think about this a little bit, but here's my offer to you. So, extra credit. Code this up. And demonstrate that it's working. You'll have to think about what that means. How would you verify to yourself something is sampling from the correct distribution? So I'm going to let you do a little bit of mental exercises, but I can help you answer this after you put some thought into it. So this will be something like a 1 to 2 page write-up. If you do this, I'll give you 10% midterm credit. You can turn this in at any point during the class. So you can turn it in tomorrow, you can turn it in on the last day. You could send it to me with your final. So you have a lot of time to think about this. Keep in mind you have another computational homework. I'll talk about it on Friday a little bit, but it's already up. But it's basically a simulation study comparing 3 different methods: the delta method, Bayes, and the bootstrap. I'll walk you through that on Friday. So somehow we'll verify that this works, but the first question you might have is how do you pick G? So G has to be chosen to adhere to this constraint, which sounds like a hard problem. So I cannot introduce values into this thing right here such that the vector of xi's that I'm plugging in to these 2 equations have an average that's anything different than x bar, the value experimenter 1 gets to see. So how would you pick G? This is the assignment, essentially. This is all MCMC assignments. Pick G. Okay, let me ask you this. How would you initialize everything? This is maybe a different question. How would I initialize everything so that I had a vector of numbers such that their empirical average was X bar, the number that experimenter 1 gets to see?
You could set them all to X bar.
Yeah, I love that. Set them all to X bar. So you might take xi0 for my initial step is equal to X bar and for all I. Good strategy. I don't even have to think about it. So I start out with everything being equal to X bar, and you can verify probably in your head real quickly that the average of that is X bar. What else would it be? So that's right. We know that that probably is not distributed according to this distribution, that everything is stacked, and in fact, with probability 0, that would happen, because these are still continuous realizations. So that initial draw is not a sample from that distribution. But as I click through this and I run it for a long time, eventually I'll obtain samples from this distribution. So now let's move on to G. How would you pick the proposal? To kind of wiggle these things around. And we're going to, through each iteration, keep wiggling everything until eventually, using this decision rule, in enough iterations, this thing will, all these xi's will be distributed according to this distribution. I'm calling it F. Here's what I would do. So I'll do a lot of your work for you right here. And again, you don't have to do this. So here's a G. So G of X star, given where I was last time. So I'm going to take my previous draw, and in my first iteration, I'll just be starting with all the X bar, all the Xi's are X bar. So what I might do for this is I might say this is equal to X t minus 1. I'm just going to enumerate this. X t minus 1, 2. I'm not going to be done writing for a minute. I'm going to say X I t minus 1. Give myself some room. Dot, 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 to xj t minus 1. Dot, 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 to xn t minus 1. So right now, this vector right here is exactly my old iteration. So I probably don't want to use that over and over again. It will not converge because it doesn't move. So what I'm going to do with this is I'm going to add an epsilon here, and I'm going to subtract an epsilon right here. Where epsilon is going to be maybe normally distributed. And there's going to be some tuning variance. So this is something you tune. Basically says how far you want to wiggle this vector. So this is a very straightforward, it's a slow moving proposal. It barely moves. So that means you're going to need a lot of iterations to get this thing to eventually work. But you can verify that this still has average X bar. If I seeded it and started it out where everything sums to some of the xi's, the average is X bar, this will also have average X bar. I subtracted something off and I added something. So what did I really do to generate this right here? My proposal is actually just this thing right here. So this is the stochastic element to the proposal. So the proposal is really that. So what would I do in here? I would take for my proposal right here, this would be a normal distribution with this epsilon right here. And you can ask yourself, this is your thinking exercise, is how do I go backwards? And that's what this is. It's the reverse proposal. So it's the hypothetical question, if I were sitting here, x star, if I accepted this vector, then how would I go backwards? And basically, you just reverse those epsilons in everything. And so this is just going to be 1 over 2 pi psi square root e to the minus 1/2 epsilon squared divided by psi squared. So this is my proposal. So I always think in MCMC, how do I move whatever my state is and try to move it in a direction so that eventually I start hitting my target. And this will get me there. You could be more ambitious. I could generate a whole bunch of epsilons and add and subtract them from 2 different numbers. And I try to move the vector a lot. So if you move it too much in one step, there's a good chance that this ratio right here isn't close to 1. So you have to be careful there. So if I try to do too much moving all at once, then maybe I won't accept my moves very often. So there's a difficult part of MCMC or Metropolis-Hastings, and it's kind of a Goldilocks phenomenon. You want to move enough, but not too much. And you don't want to move too little. And so some of that is determined by this psi squared. If you do use this proposal, it turns out the reverse has exactly the same distribution and they cancel each other. I'll let you verify that. The one I just gave you is a symmetric proposal. It cancels, and if you use this proposal, and convince yourself of that, this ratio is going to be 1, and then all I'm left with in this ratio is the ratio of my targets. That's kind of a nice thing. All stuff you can think about, and we can talk about more in review. Jenny?
Professor, do you have to do some sort of sampling to select which index to
Oh, yeah.
apply?
Good question. Yeah, I skipped a step. So I need to flip a coin and select I and select J. So probably, here's what I'm imagining, is I might select I and J uniformly. And if I select I and J uniformly, that would be part of my proposal ratio, but a uniform divided by a uniform is constant as well. And so if I selected them uniformly, then they would also cancel out of this ratio. All things you'll convince yourself of. So I and J is going to be a uniform between 1 and n. So both of those will be selected uniformly. You might ask the question, what if I got I and J exactly the same numbers? You wouldn't be moving the vector at all. And so what would actually happen if you did that? This would be 1. If I didn't move the vector, that's that. So this ratio would be 1, and you would accept a move. I wouldn't put a reflection in there and account for it and try to constrain everything so that they're always, I would just probably let that happen periodically because it'd be easier to code up. If you wanted to make it a little bit more efficient, you could try to constrain it, but you'd probably have an if statement in your code, and checking that condition at every step would take time. Sam, you had a question now. Was that it? Something like that. Yeah. All stuff we can spend more time talking about later. This is supposed to provoke you and pique your interest in terms of sampling algorithms. But I like it, because if experimenter 2 was going to draw these numbers, how would they do it? Now you have an algorithm. You need to run this for a long time. And keep in mind, early in this Markov chain that you're forming, it's Markov because it only depends on the previous sample. Eventually, it converges to having samples from the target distribution. And so you need to find where they actually converge. And I can give you some diagnostics in review to help you think about that. Here's another problem that you can do. If you want to gear yourself up for doing this problem that might be a little bit complicated for your first Metropolis-Hastings exercise, here's another problem you can work on. So this will be 5% midterm credit. And I'll offer these to you periodically. So if you do blunder the midterm on a question and you're like, my life is over because I had a temporary lapse of reason and I couldn't answer question number 4. You know, oh my goodness, it was 25% of the midterm, now I'm going to fail this class. That's not going to happen. Lots of pathways to get an A. So this is the way you get forgiven. If you want to just challenge yourself, you can do that anyway. 5% midterm credit. Apply Metropolis-Hastings to problem 5.68A in the book. And here's the proposal you're supposed to use. So remember, the goal is to sample a t-distribution from a t distribution. It's going to have some arbitrary number of degrees of freedom, so you probably want to make that arbitrary and change it and see how your algorithm works for various degrees of freedom. So apply Metropolis-Hastings, problem 5.68, so this is a t-density. This will have new degrees of freedom. This is your target. So this is F in that ratio, and I'm going to give you the proposal. So with proposal, this will look like this. G of X, I'll say X star is distributed according to this thing, and we're going to make it Markovian. They give you an independent proposal in the book. They say use a normal, and it's a static normal. And a couple of you figured out that is not a great idea. So that turns out to be a poor proposal. It doesn't sample things in the tails of the t-distribution very often. And so while theoretically that proposal will work in practice, it doesn't work very well. So it actually takes you an infinite amount of time to learn about the tails of that distribution, especially if you made the degrees of freedom relatively small. So this thing right here, we're going to say is a normal distribution. I'm just going to write it down. 1 over 2 pi, there'll be some proposal variance. E to the minus 1/2, this will be X star, minus X t minus 1 squared over psi squared. So the way that we're going to propose new values, right here, I'll put the X star in here if you'd like. Usually I leave that as a dummy variable, but just so you can see where you plug things in the equation. If you use this proposal, it's saying your proposed value is going to look something like your previous location, but I'm going to add a little bit of jitter that's controlled by this tuning parameter. If you use this proposal, then in the Metropolis-Hastings ratio, the inverse proposal ratio cancels. This actually is a random walk, and it'll allow you to move up and down those tails of the t-distribution. So same exact assignment. I want you to code this thing up, give me a 1 or 2 page write-up, and you're supposed to demonstrate that it's working. This one's a lot easier to demonstrate because I can check at the end of it if all my samples are t-distributed. And you can do that real easily with a QQ plot because this is one-dimensional. I'll give you some performance diagnostics in a review session. Probably not this next one. We'll probably focus on the midterm. So you also will have until the end of class to turn this in. So that's 15% on all. Okay, so that should alleviate you a little bit. Any questions? I probably shouldn't ask that because I'm sure there's lots of them. If there's not a lot of questions, you're just not thinking about this that much. There's an infinite set of questions, and it all concerns G, and all my answers will always be, it depends on what F is. So different types of Fs require different Gs for the algorithm to perform well. Not all is lost. A lot of Fs have similar structure to them. So there's certain phenomena that creeps into problems all the time, and after you experience this for a while, you get good at picking Gs. There's whole books on it. Okay, I'm going to move on. Let's just do the factorization theorem. So I'm going to do one side of the proof. So the factorization theorem says this. T of x is sufficient if and only if my distribution f of x given theta, so this is the joint distribution, can be factorized like this. H of x G T of x given theta. So it's going to factorize into a component that only involves the data, and then a component that involves the sufficient statistic and the parameter. If we think about this a little bit, that's kind of obvious from what we've already done. We see that things factorize and it cancels, and that's what's making that ratio a constant. This is actually how I think about sufficient statistics. So if I'm looking at a model and trying to identify the sufficient statistic, I'm trying to see this part of it and trying to think in my head how I get this part to factorize out. What this says is that there's a part of your distribution that you cannot separate out from theta. And so in our case, that was the x bar minus 1 squared term. Let's just ask a slightly different question. What do you think is sufficient for sigma squared? I'm going to just point to it. We treated sigma squared in the previous problem as a constant. We weren't thinking about it too much. But if we look at everything, it's actually going to be this term that's going to identify what's sufficient for sigma squared. There's a part of the data that I can never factorize away from sigma squared. What part can I not factorize away from sigma squared? It's this. So sum of the xi's minus x bar squared. And most of you know that you'll divide that by n or n minus 1 to come up with an estimator of sigma squared. And so it's the part that you can't factorize away. So I kind of like this problem because we can also ask the question about sigma squared and turn it on its head, think about a different question. So it's always, what part of the data can I not factorize away from the parameter I'm trying to estimate? So we're going to do the only if part of the proof next time. Well, let's just knock out the first part of the proof. And so what we'll do is we'll prove that if T of x is sufficient, this factorization exists. We'll do that in just a minute. And then we're going to say if this factorization exists, it implies T of x is sufficient. We'll do that second part next time. But let's just note it. If T of x is sufficient, so this is the if part of the proof, and we'll do the only if part next time. Then I can write out f of x given theta is equal to f of x and T of x. Same step that we did last time. I'm going to include the sufficient statistic. No extra information because I compute it directly from x. There's no randomness here. This is f of x given T of x and theta times f of t of x given theta. T of x is sufficient, so this doesn't depend on theta. Same step that we did last time in the two experimenter proof. And so if I write this down, there's no theta right there. And I like this proof because it's very constructive. It shows you how to come up with the factorization. You just do that. This right here is h of x. It only involves the data, and this is g of tx given theta. So the book makes mention that g and x don't have to be distributions, but the way we've applied it is we made them distributions to identify h and g. This is what I'm actually doing. I'm just thinking about how do I factorize everything and what can I get away from the parameter, and if I can't get it away from the parameter, it's part of the sufficient statistic. Next time we'll come in with the only direction. We'll say the factorization exists, and then we'll prove whatever is in that g component has to be sufficient. That's it for now, you guys. So hopefully I'll see you tomorrow at 5:30. If you have any other questions, I'll stick around for a little bit. I'll see you either tomorrow, but if not, I'll see you on Wednesday.